Hey folks, my name's Nathan Johnston, and welcome to Lecture 15 of Advanced Linear Algebra. Today we're going to talk about properties of linear transformations. So the idea is we're going to think back to all of the properties of matrices that we learned about back in introductory linear algebra, and we're going to see how we can generalize them so that they apply now to arbitrary linear transformations. Okay, and we're going to focus in particular on the range, rank, and eigenvalues and eigenvectors of matrices and linear transformations now. Okay, so the general theme going through all of these properties is that really nothing changes. We just take our definition that we had for matrices and just sort of replace the matrices with linear transformations, and everything works out. Okay, and we're going to see that you can compute these things via the definition, working sort of abstractly with linear transformations, or you can compute these things by representing those linear transformations as matrices, and then just using all the techniques that we already learned in the previous class to compute those properties of the standard matrices, and everything works out the same. All right, so let's go through a couple definitions to get us going here, and then we'll go through a couple examples of how you actually compute these things and get your hands on them. All right, so if you haven't looked at the range, rank, or eigenvalues or eigenvectors of a matrix recently, I really recommend before you go through the rest of this video that you review those concepts from introductory linear algebra. Okay, so make sure that you understand and know what the range of a matrix is, the rank of a matrix is, and what an eigenvalue and eigenvector of a matrix is before you go through this version for linear transformations. All right, so starting off with the range of a linear transformation. It's basically the exact same as what it was for a matrix. Remember, for a matrix, the range of a matrix was the set of all output vectors that you could get if you did matrix times vector. Okay, for linear transformations, it's the same. The range of a linear transformation, it's the set of all possible outputs of that function, right? If you plug in every single vector v from the input space and then collect all the outputs that you get, all the vectors of the form t of v, that gives you the set that we call the range of that linear transformation. Okay, and if that linear transformation is sending vector space v into another vector space w, then this set here, this range, it's a subspace of w. Okay, so it's obvious that it's a subset of w, right? Each of these vectors lives in w, so this is a collection of vectors from w, but actually it's a subspace as well. Okay, so it satisfies those subspace properties. Okay, if I add up two vectors in the set, it's still in the set. And if I scale or multiply one of the vectors in the set, it's still in the set. So that's just an exercise to show that, but it is a subspace of the output space of the linear transformation. Okay, and back for matrices, we said that, hey, the rank of a matrix, well, there are a boatload of different ways to characterize it, but one of the ways of characterizing the rank of a matrix was it was the dimension of the range of that matrix. So we're just going to do the exact same thing here for linear transformations. The rank of a linear transformation, we're going to say that it's the dimension of the range of that linear transformation. And this makes sense because, hey, this range, it's a subspace. So in particular, it's a vector space, so it has a dimension. Okay. Next up, the null space. We're not going to do a whole lot with the null space yet, but the null space of a linear transformation, we can talk about that as well. It's, again, the same idea as it was for matrices. It's just the set of all vectors that get mapped to 0, right? The null space of a matrix was the set of all vectors such that a times v equals 0. Well, now we're working with linear transformation, so it's the set of all vectors such that t of v equals 0, okay? It's the set of all vectors that get squished down to the 0 vector. And again, this is a subspace, but this time it's the subspace of the input space, right? It's the collection of all input vectors that get mapped by t to the output vector 0. So it's a subspace of the input space. And again, so it's obviously a subset of the input space. The fact that it's a subspace, though, again, you have to check those two subspace properties. You have to check that, yeah, if I add up two things that get mapped to 0, it still gets mapped to 0. If I scale or multiply something that gets mapped to 0, it still gets mapped to 0. So again, there's a bit of an exercise there to show that this really is a subspace. All right, and then the last property of linear transformations that we're going to introduce right now is eigenvalues and eigenvectors, okay? And again, exact same idea as it was for matrices, okay? So we're going to say that lambda, this is some number, this lives in whatever field the linear transformation t is acting on, so whatever the ground field is. We say that that's an eigenvalue of t if there's some non-zero vector v such that t of v equals lambda v, okay? And this non-zero vector v, that's called the corresponding eigenvector of lambda. Okay, now this is the exact same thing that we had for matrices. For matrices, we had a times v equals lambda v, and the idea was a just stretches that vector v by whatever the scalar lambda is. It stretches it by a factor of lambda, but doesn't change its direction. Okay, and it's the same thing here, same intuition with linear transformations. What's happening is if I apply the linear transformation t, well then that vector is just getting stretched, but it's not sort of getting moved around the vector space other than that. It's not getting rotated or turned in some other direction. It's got the same direction, it's just stretched by a factor of lambda. So those are eigenvalues and eigenvectors. All right, so first question is, well, how do you compute all of these things? How do you work with them? And the idea, we're not even going to prove this. The idea is just exactly the same as it was for invertibility. How did you determine if a linear transformation was invertible? You forgot about linear transformations, just worked with matrices instead. You just worked with a standard matrix and answered the question there, okay? It turns out for all of these properties here, you can do the exact same thing. Just work with the standard matrix and you can find out what the range of your linear transformation is. It's the range of the standard matrix, as long as you sort of suitably represent things in a basis. Was the rank of a linear transformation? Well, it's just going to be the rank of the standard matrix, and so on. You can find eigenvalues of a linear transformation just by computing the eigenvalues of a standard matrix. All right, so let's see how this works. Let's go through a couple of examples here. All right, so let's find the eigenvalues of the transposition map, right? Like the map that sends a matrix to its transpose, working specifically with the 2x2 matrices this time. All right, so the transpose map, it acts on the space of 2x2 matrices, spits out another 2x2 matrix. Let's find its eigenvalues and corresponding eigenvectors, okay? So there are a whole boatload of ways that we could do this calculation. The first way that we could do it is directly via the definition. So we go back up here, the eigenvalues and eigenvectors, they're the things that get sent to a scalar multiple of themselves via this linear transformation. Okay, so let's do that way first. So here, linear transformation is acting on M2, so here's just some arbitrary member of M2. All right, well, if T of A equals lambda A, what's that mean? Let's write it down a bit more explicitly in terms of matrix entries. Well, what that means is transpose of A equals lambda A. Okay, so here's transpose of A. I've just taken the transpose, which swaps the B and the C, right? Leaves A and D alone, they're on the diagonal. And then lambda of A, well, you just multiply every entry by lambda and you get that matrix over there. So these matrices have to be the same as each other if, A is an eigenvector corresponding to eigenvalue lambda. Okay, so here, this really is a system of 4 equations. They're not quite linear because we've got variables multiplied together, but it's 4 equations. Just match up entries. A equals lambda A, C equals lambda B, B equals lambda C, and D equals lambda D. So we get these 4 equations here. And if you go through and solve that, there are only 2 possibilities, okay? So if you focus on this first equation, for example, A equals lambda A, the only way that can be solved is either lambda equals 1 or A equals 0, okay? And then you split into 2 cases from there and you can solve the rest of the equations fairly simply once you split into those 2 cases. So the first case, if lambda equals 1, well, you're going to find, okay, D equals lambda D, great, that guy's satisfied. And then here, the middle 2 equations, I just need B equals C. All right, so what's that tell me? It tells me that, yeah, lambda equals 1, that's an eigenvalue. And what are the corresponding eigenvectors? Well, they're just the matrices that have B equals C. In other words, they're the symmetric matrices. The eigenvectors corresponding to lambda equals 1, they're the matrices that have these 2 off-diagonal entries equal to each other. Those are called symmetric because they equal their own transpose. All right, what about the other case? Well, if A equals 0, all right, then you can just sort of trace through it. A similar argument shows that D's got to equal 0. And then you just look at the 2 middle equations here. The only way that you can get at least one of B or C not equal to 0, remember eigenvectors can't be 0, so you can't have all 4 of A, B, C, and D equal to 0. The only way to get at least one of them not 0 is if lambda equals -1. And what's happening is B equals minus C, and then C equals minus B, okay? So this is the only other possibility. Lambda equals -1, that's also an eigenvalue of the transpose map. And this time, we need the diagonal entries equal to 0, and the off-diagonal entries are just negatives of each other. Okay, so lambda equals -1 is also an eigenvalue, and this time the corresponding eigenvectors are the matrices that have 0 here, 0 here, and the off-diagonal entries are just negatives of each other. And those matrices are called skew symmetric, right? Their transpose is just the negative of themselves. All right, so those are the skew symmetric matrices, and those are the eigenvectors corresponding to eigenvalue -1. All right, so that's one way that you can find the eigenvalues and eigenvectors of the transpose map. Another way that you could find the eigenvalues and eigenvectors is to work with the standard matrix of the transpose map. All right, so let's think back. We computed the standard matrix of the transpose map already, fortunately. We did this last week, okay? So if we start off with the standard basis, which I'm calling E here, if we start off with the standard basis of the 2x2 matrices, then the standard matrix of T with respect to that standard basis is just this guy here. It's got one, it's almost the identity matrix, except things are sort of swapped around in the middle there a little bit. Okay, and now what if we went ahead and we computed the eigenvalues of that guy instead? Well, it's going to turn out, well, first off, I mean, eigenvalues in general, 4x4 matrices are kind of ugly to compute, but fortunately, because there's so many zeros in this matrix, you can compute them fairly straightforwardly via cofactor expansions, okay? There's so many zeros that the computation actually isn't that bad. You can do it just straightforwardly by hand, and you're going to find that the eigenvalues are, you're sort of getting a 1 eigenvalue from here, a 1 eigenvalue from here, and then the central 2x2 block is giving you another eigenvalue of 1 and also an eigenvalue of -1. So you're going to find your eigenvalues are 1, 1, 1, and -1. So in other words, 1 with algebraic multiplicity 3 and -1 with algebraic multiplicity 1. Okay, and of course that exactly agrees with the answer that we found up here. Up here we had eigenvalues 1 and -1. Here we get the exact same thing, and that's always going to happen. Your standard matrix will tell you what the eigenvalues of the original linear transformation were. That always works out. There's a theorem there. And it's not hard to prove, it's just tracing through all of the definitions. All right, let's do it a different way. Okay, another way that we could do it is via a different standard matrix, right? Again, keep in mind, there are all sorts of bases of every vector space. There's all sorts of bases of the space M2 of 2x2 matrices. So we didn't have to use the standard basis here. We could have used the poly basis. Remember, the poly basis is this weird basis that we saw at the end of week 3, and we computed the standard matrix of T with respect to this poly basis, and it ended up having this form. So it still represented the same linear transformation, just in a different basis, okay? And notice that, hey, this matrix is not the same as this one, so we might be a little concerned, oh, it's a different matrix. But the eigenvalues are still going to be the exact same. In particular, this standard matrix is diagonal, and we have a theorem from introductory linear algebra that says your eigenvalues of any diagonal matrix are just those diagonal entries. And what are the diagonal entries? 1, 1, 1, and -1. So again, we get eigenvalues 1, 1, 1, and -1, which is exactly what we would expect. Even though the matrix representation is different, sort of all of the important properties of it are going to be the same. In particular, eigenvalues are going to be the same. All right, so we have a whole boatload of ways that we can compute eigenvalues of linear transformations on finite dimensional vector spaces now. All right, great. Let's do another example, this time computing the range and the rank of a linear transformation. In this case, the differentiation linear transformation acting on degree 3 polynomials, okay? So the linear transformation that takes the derivative of a degree less than or equal to 3 polynomial. Okay, again, you can do this in different ways. Method 1 of doing it, you can just work directly from the definition, okay? To find the range and rank of this linear transformation, just write down, well, what is the range? Well, the range, it's all possible outputs of that linear transformation. So I plug in everything from P3 into that linear transformation. So I'm plugging in every degree 3 polynomial into D, and I'm collecting all the outputs together. All right, well, what does the output look like? Derivative of just some degree 3 polynomial looks like this. I just took the derivative, right? The a goes away, bx becomes b, cx squared becomes 2cx, and so on. All right, so the range is this set here. It's the set of all polynomials of this form. But what polynomials can be written in that form? Well, every polynomial of degree less than or equal to 2 can be written in that form. I mean, the coefficients are kind of weird here because it's 2c rather than just a c, and it's 3d rather than just a d, but every polynomial of degree less than or equal to 2 can be written in that form. Right? So the range of the derivative linear transformation is just p2, the set of degree less than or equal to 2 polynomials. All right, what about the rank? Well, again, if we're working straight from the definition, the rank of the derivative is just the dimension of its range. That's the definition of the rank of a linear transformation. All right, well, what is the range? Well, it's just P2. We just computed that. So we just plop that in here there. So we want the dimension of P2. And we know that from a couple weeks ago now. The dimension of P2 is 3. So the rank of this differentiation map is 3. Okay, well, we could also try computing this from a standard matrix instead. What if we don't like working with abstract linear transformations? What if we like working with matrices instead? Fortunately, all of our tricks for working with matrices still give us the right answer. So we just pretend we're in introductory linear algebra and everything will work out. All right, so let's instead represent this differentiation map via a basis. And we might as well use the standard basis just to make things simple. All right, then the standard matrix of D with respect to the standard basis, well, it's just this guy here. And this is just a straightforward calculation. We actually went through it either last week or the week before, sometime recently. All right, so this is our standard matrix of the differentiation map with respect to the standard basis. And now we just do things that we did in introductory linear algebra. What is the range of this matrix? Well, we have the theorem from intro linear algebra that says the range of a matrix is the span of its columns. So span of this guy, well, the zero vector doesn't contribute to anything to the spans, so forget about it. And this guy, and this guy, and this guy. And these scalars don't really matter. The 2 and the 3 don't affect the span at all, right? So the range of this matrix, it's the span of these columns here. In other words, it's just the span of E1, E2, and E3. It's just the set of all vectors in 4-dimensional space that have that have entries in the first, second, and third entries, but then zeros in the fourth entry. All right, so that's the range of the matrix, and that sort of corresponds to the fact that the range up here was P2, right? The range up here was just everything that can be written as a linear combination of 1x and x squared, but then no x cubes. Well, same thing here. We have this E1, E2, and E3 sort of corresponding to the first 3 basis vectors, but then none of the fourth basis vector. All right, what about the rank? Well, the rank of this matrix, just go ahead and do your Gaussian elimination. Remember, one way of computing the rank of a matrix is you do Gaussian elimination on it, get in row echelon form, and count the number of non-zero rows. Well, this is already in row echelon form, and there are 3 non-zero rows. The rank is 3, which of course matches the answer that we had up here. Another way of looking at the rank of a matrix is the dimension of its range. Well, the dimension of the range is again 3. It's the span of these 3 linearly independent vectors. So the rank is 3 as well, which again matches what we had up here. And that will always happen. Even if I used a different basis to represent my derivative linear transformation, you're going to get different matrix representations, but the rank is always going to be the same. All right, so that does it for today's class. Next class, we're just going to carry on with properties of linear transformations, but we're going to do a really neat application of it involving, things like taking the square root of a linear transformation, and we'll learn how to do some fractional calculus with these ideas. So I'll see you all then.